In many situations during Rust coding, we don't directly handle primary data. Instead, this data is organized into structs. For example, we can organize the coordinate data into a pair wrapped in a struct. Another example is the Caterpillar game we developed in our previous videos, where we control a sprite named Caterpillar to catch targets carrying letters to build a word. Chimpanzee. The positions and speeds of the sprites are floating point data wrapped in structs. The struct game and its associated methods depict the rules of the game. Before we delve into the topic of lifetimes, we will define some structs that wrap primary data types and can act as toy data for our example code. What is a lifetime in Rust? In Rust, all references have an attached lifetime, which is part of the type. A lifetime is a concept used to ensure that references in the code are valid for a certain duration. Lifetimes help prevent issues such as dangling references or memory leaks by specifying how long a reference is valid within the program. This ensures that references are only used when they are guaranteed to be valid, improving the safety and reliability of the code. Rust has rules that allow lifetimes to be omitted in certain places where the compiler can determine a suitable default choice. Let's examine the following simple example. The code compiles successfully. What is the lifetime of the input reference? Let's pretend to be the compiler and apply the lifetime elision rules. The three elision rules. Rule 1, each input reference gets its own distinct lifetime. Applying the rule, we have here tika is a lifetime parameter. Let's see how lifetimes work on structs. When compiled, the code resulted in error E0106. Unlike function signatures, struct definitions require explicit lifetime annotations when holding references. Here is an example that requires writing a function that prints either foo1 or foo2 based on their values. The function compares the values of two instances of struct foo and prints the one with the larger value. The code compiles successfully without any errors, even without providing any lifetime parameters. Let's pretend to be the compiler again and apply the rules. Compile and run the program. There is one problem: we are asked to print the instance of foo, not the field of the instance. So we edit the code and compile it. We need to change the print line format. It failed again. After deriving the debug implementation, the code compiles and runs. A function does not require an explicit lifetime annotation if it does not return a reference in its arguments. What happens if a function returns a reference? Let's apply the three rules to infer the lifetimes for the input references and the returned reference. Even after applying rules 2 and 3, the compiler is still unable to infer the lifetime for the output reference, resulting in an error message. Explicit lifetime annotations are needed in this example. In addition to a single lifetime, two lifetimes can also work as long as the lifetime for the output reference does not outlive the lifetimes for the input references. The code compiles successfully. Furthermore, it is possible to use 3 lifetimes. In this example, we will discuss how to annotate lifetimes on methods. The methods can be treated as regular functions and follow the elision rules. It is important to differentiate between self, with a capital S, which is the type of the current object, and self, with a lowercase s, which refers to the instance. Let's add a field to the struct Baz and define 2 objects of Baz, A and B. We want to compare the values of A and B. The code will fail to pass the elision rules, so explicit annotation is needed. What happens if the struct foo holds a reference, and we want to pass an instance of foo to a function as an argument? The code will not compile. After making the necessary modifications as suggested, the code compiled successfully. If we remove the lifetime annotation for the inner reference of foo, it still compiles. Why? I asked ChatGPT for an answer. In the given code, the struct foo contains a reference to a U8 value. The function getX has a lifetime parameter for the reference f. However, the inner reference f.x is not explicitly specified in the function getX. This raises the question, why does the code compile successfully when the function getX expects 2 lifetimes? Here, I have only highlighted the key information from the answer. The compiler knows that f has a lifetime of a, f.x inherits the same lifetime a. Please pause the video to read the highlighted text. This is the answer adopted from Llama 3.3. This is the answer from DeepSeek. According to DeepSeek, the lifetime in the function signature is correctly inferred to match the lifetime of the reference fx. In addition to the suggested correction by the compiler, 2 lifetimes also work. I asked ChatGPT for an answer. I am not going to go through the answer page by page, instead, I will summarize key points alongside the code. Y lives for the entire scope of the main function. Q.x is a reference to y, so it has the same lifetime. The lifetime of the reference of Q is 2. Lifetime 2 must not outlive lifetime 1. Make sure that the inner reference, x, outlives the outer reference. If we change the lifetime of the output reference, the code still compiles successfully. Why? ChatGPT provides 2 responses. The reason the code works is the same as we just saw. Next, let's implement a method that has the same functionality as the function get_x. This code does not compile. After making the suggested modifications, it compiles successfully. The use of an unnamed lifetime implies that the struct foo has an associated lifetime without explicitly naming it in the impl block. Alternatively, we can use a named lifetime, and the code will still compile. It is not necessary to explicitly annotate the method get_x, but if we do, the code will still compile. Please try to compile and run the program.